Okay, guys, this is a quick summary of buoyancy and the buoyant force. Um, for more detail, you can read the text, but I want to give you just a summary that's going to enable you to uh, work on some of your problems for homework. And so, buoyancy that refers to things that are floating in a fluid. And so, you should be familiar with, if we take an object. Let me switch colors. So we have fluid, and we're going to take some object and we put that object into the fluid. Then when it gets placed into the fluid, the water is going to rise. So the new level, would come up here or something. So say it's completely submerged. And what's happening is this object that we placed into it is displacing an equal volume of water. So we get a displacement of water, or a fluid, I should say. It's displacing an equal amount of an equal volume of fluid. And this is what we're gonna kind of work with, is this idea that dealing with the amount of fluid that's been displaced and the volume of the object. And so there's a couple different cases. Let me just draw. So suppose we had a fluid like this. So we could have an object which is, partially submerged. So there's a little piece of it. And then we could have it kind of, well, I guess there's only two cases. And then the other case would be it's completely submerged. Or here, let's do this. So here a little bit of it is submerged, here most of it is submerged, and then we can have it completely submerged. So three cases that we can think about. And the idea that what we're going to focus on is the amount of volume, the volume of the fluid that's being displaced. And so over here with this one, we can see that it's only displacing this little amount. And here we have a bigger volume which is being displaced that's supporting it. And here it's displacing all of it. It's displacing the whole object. And this is what we're going to be using when we talk about buoyancy and the buoyant force. And it's essentially that, if an object is floating like this, then we know that the net force on this is zero. So we know that the force of gravity here has to be counterbalanced by something, and that's the force pushing up, which we'll call the buoyant force. Put an FB or a B for buoyancy. And this force that's being exerted is exactly it's the weight of the water that's being displaced here. So that buoyant force is equal to the weight of the displaced water, or fluid, I'm sorry. I keep saying water, but you know what I mean, right? Displaced fluid. So we would say that the buoyant force is equal to the weight of the fluid. So weight, remember, is mass times g. So the buoyant force in this case is going to be the mass of the fluid times g. Now, it'd be nice if we just knew like the mass that's being pushed out here, but we typically won't. And so we have to use density in order to get that. So we're going to be using the definition of density over and over again, which is mass over volume. Because typically we'll know the density of a fluid. And so if I multiply across, I get the density of the fluid times the volume is equal to the mass of the fluid. And then this we can take and substitute back in. So we'll get that the buoyant force is the density of the fluid times the volume being displaced times g. And so this is Archimedes' principle, this part right here, that the buoyant force is equal to the weight of the displaced fluid. And then it's counteracting, so let's just analyze this one. So again, this was just to kind of build this idea of the buoyant force. But if we wanted to actually analyze the situation, then we'd have to use Newton's laws. So for instance, here the net force is equal to zero. So we get the buoyant force, which is up, minus the force of gravity, equals 0. So the buoyant force, which is this, so we would get the density of the fluid times the volume times g is equal to the mass of the block times g. So the g's cancel, and then we can work from there, just depending upon the problem. So then the question is, which one of these has a greater mass? We don't know because we don't know the shape, but what we do know is that the density of the object, so the density is increasing, because density is going to determine what floats and how much of it floats. So as long as the object is less dense, so the density of the object is less than the fluid, then it floats. If it's exactly equal, then it'll be in equilibrium. So wherever we put it, it's just going to stay. And if it's greater than, then it's going to sink to the bottom. So let me summarize that. Let me clear this page. So we can tell what's going to happen based on the density. So if the object is floating, then the density of the object is less than the density of the fluid. If the object just kind of floats underneath, it's submerged, but it doesn't sink to the bottom, so it's just kind of stable right here with nothing attached to it, then the density of the object is equal to the density of the fluid. But if it sinks all the way down and doesn't stop, then the density of the object is greater than the density of the fluid. And then how much it actually floats up here, this would be as the density of the object approaches the density of the fluid, it would sink further and further down. Okay, that's the basic idea. So dealing with buoyant forces and stuff, we're going to get into density. You're going to be using a lot of density in order to change that mass over into terms of density and volume. A common one is like a block with strings tied to it and scales and that sort of thing. So suppose we had so we have a fluid, and then we'll put a scale down at the bottom. So there's a scale there, and then we're going to lower this. It's tied to a string. Or you know what? Let's not even do that. Let's ignore this one at the bottom. So let's just have the string. So we lower something that's much more dense than the fluid, and we hold it. So this has some mass, and some block, Okay, so how would we start analyzing this? So if it's stationary, then we know that the net force on it is 0. And then we're holding with the string, and so we can then break out everything that we can, all the forces that we'll need to analyze. And so, actually, let me move this over. So what we would have is we would have our tension acting up, and of course the force of gravity pulling it down. But now we're going to have a buoyant force that's acting up as well. So I'm going to say the force of buoyancy. You can use B as well. So in this case, it would be, your net force is equal to 0. So we'd have tension plus the buoyant force minus the force of gravity equals 0. And suppose we wanted to know like the tension, how much tension is in the string. So then the tension would be the, I put force of, I messed these up. That's the buoyant force and force of gravity. Okay, so if we move this over, we would see that it's the force of gravity minus the buoyant force. So the tension is going to be the mass of the object times g minus the mass of the water times g. But here we don't know the mass of the water, so this is where density comes in. So density is mass over volume. So it'd be the density of water or fluid times the volume is the mass. And so we'll substitute that in. So we get tension is going to be mg minus density of the water times volume times g. And then from there, we would be given these values or whatever. But Setting it up, it's kind of like this step comes in pretty, or is used quite a bit. Substituting, so we get mg, the weight of the water, and then substituting it in and for density and stuff. But keep in mind that we could have multiple forces, so we're going to be using a lot of these force diagrams, and the net force is zero. That happens a lot. Anyway, that should be enough to get you started on the problems. So give them a try, and then in the next class we can talk about it and clarify any issues that you came up with while working through the problems.